Namaskar, Fundamentals of Physics video lecture series. This is my 10th talk on error, significant figures and dimensional analysis. In the previous talk, we have discussed certain aspects of measurement by taking measurement of length as an example. In the last talk, for measurement of the order of meter to picometer, we learned about certain tools like ruler scale, 1 year caliper, micrometer screw gauge, 1 year micrometer screw gauge, and a few instruments like optical microscope, transmission electron microscope, scanning electron microscope, and scanning probe microscopy. In literature, you may find mention of gamma ray microscope, but gamma ray microscope exists in thought experiments only. One of the thought experiment using gamma ray microscope was described by Heisenberg in explaining his uncertainty relationship. The gamma ray microscope, if we can make, then definitely will have better resolution because of high energy of gamma ray photon. But there are certain practical problems, and from practical point of view, the gamma ray microscope is not achievable as such. But we do make study by using content scattering, and the gamma ray when scattered by the matter or X-rays when scattered by the matter can be studied, and we can get information about the distributions of electron inside an atom, the momentum distribution. This is beyond our discussion at present. The resolution of a measurement system, as explained in the last talk, is the smallest but distinguishable, and it is different in values for different tools and different instruments. So I have explained in the last talk that human eye has angular resolution of 1 minute, which corresponds to 0.1 millimeter at the distance of distinct vision, and which means that if there are two dots at 25 centimeter away from eye and the separation between the two dots is 0.1 millimeter, then both dots would be clearly resolvable by human eye. But if you increase the separation between eye and dots, maybe at some distance, they will not become resolvable by human eye. So resolution of any instrument is very important issue, but it has no direct relation to the accuracy of measurement. For example, you may perform an experiment with high-end, say, scanning electron microscope, but if you are not familiar and if you commit mistakes in making experimental observations due to non-compliance of the protocol or any other reason which causes the error, then you may find that though the list count is better, the accuracy you will not be able to achieve in the course of measurement. So list count or resolution is not a parameter which is directly related with the accuracy of measurement, and however we expect that high resolution instruments would enable us to make more accurate measurement, but due care is to be taken in the process of measurement. In this talk we will discuss some of the aspects related to it. What is accuracy? Accuracy refers to the closeness of a measured value to a standard value or already known value for that measurement, or what is called true value of the measurement. So it is believed that there is a standard or known or true value, and the outcome of the experimental measurement should provide us that value. But in actual case, what we find that the measured value is close to it but not equal to it. So accuracy refers to how close the measured value is to the standard or norm or true value. I will give you an example. For example, standard value of speed of light is 299,792,458 meter per second, and if measured value in an experiment is say 300,000,000 meter per second, then you can determine by subtracting the standard value from the measured value the error in the measurement. So error in the measurement by definition is measured value minus the standard or norm or true value. So in this particular example, we find that error is plus 207,542 meter per second, and it means that this measurement involves a 0.07% error, or one can say that it is 99.93% accurate. Therefore, it is quite clear that if in doing calculation you use the value of speed of light as 3.0 into 10 raised to power 8 meter per second, which we generally do for simplicity of calculation, then what you have done is that you have used a value which involves 0.07% error, and therefore it will have a bearing on accuracy of your theoretical calculated value too. And this should be noted that if we are interested in having more correct expression or value for a particular quantity using the speed of light, then the standard value of the speed of light should be used. Accuracy, however, can be improved through the experimental methods. First, by making each single measurement more accurate, and that can be done also by ensuring that the systematic errors get minimized. So one of the objectives of improving accuracy is that true value and the measured value are close, and the error is responsible for the difference in the true value and the measured value. One of the major source of error is called the systematic error. So in course of measurement, we have to ensure that the systematic error get minimized. The other cause of concern for error is the random error, and we also want to reduce random error. That can be reduced easily by making repeated measurements and taking the average value of all measurement as the final result in place of treating an individual measurement as the result. So the accuracy can be improved by minimizing the systematic error and as well as the random error. But if you perform an experiment in such a manner for measurement that it involves blunders or gross errors, then the accuracy would be badly affected. Blunders or gross errors cannot be permitted in scientific deliberations, and therefore you should avoid blunders and gross errors in experimental measurement. And if it happens, then the particular data which is involving blunders or gross error should not be considered for determining the average value if you are using repeated measurement to minimize the random error. It is possible that when you make measurement of the same quantity by say two different processes involving maybe the instruments of same resolution, say A and B. So A and B are having same resolution and are measuring the same quantity but are employing say two different processes, and the different processes also may mean different persons performing the measurement. Then it is possible, or different instrument also, then it is possible that A is more precise and more accurate than B, or the opposite, A is less precise but more accurate than B, or A is more precise and less accurate than B, or A is less precise and less accurate than B. So all four possibilities are there, and they can be combined, like A is more precise but less accurate, or A is more accurate but less precise. In this manner, we can say that the measurement, and in case of measurement, the accuracy and the precision are mutually distinct aspects of measurement. However, generally with better resolution, proper calibration and careful measurement, following the protocol strictly, observing all precaution, both the precision and accuracy can be achieved in better manner. So if length is measured using a vernier caliper of list count 0.01 millimeter with no zero error, proper care in place of a ruler scale which has the list count of 1 millimeter, then we expect that the precision and accuracy in the measurement by vernier caliper will be better than the precision and accuracy in the measurement by the ruler scale. If you measure, for example, the length of a AAA size battery by using vernier caliper and ensuring the minimization of systematic errors and that of random errors through repeated measurement, you will get better accuracy than by measuring it using a ruler scale. Since it has a standard value of 44.5 millimeter and ruler scale has a list count of 1 millimeter, vernier calipers generally has a list count of 0.05 millimeter, better than the ruler scale. So can be chosen to measure it with more accuracy required for making use of such batteries in the gadgets. If the length is more than the standard length, it may cause problem in use of such batteries in the gadget. So what we note that vernier calipers can provide us more accurate result than the ruler scale in most of the cases. Is vernier calipers also a precise tool for measuring length of AAA battery? And for answering that question, for understanding that, we need to understand what is precision. Precision refers to, in case of many measurements which you make for minimizing the random error, precision refers to how close measurement of the same item are to each other. So, if the minimum value in repeated measurement of AAA battery length is say 44.45 millimeter and maximum value is say 44.55 millimeter. So the values are in the range 44.45 millimeter to 44.55 millimeter, and the range is the difference between maximum and minimum is of 0.1 millimeter. It is highly precise, and what you may find that if you make the measurement using ruler scale, you are getting the minimum being 44 and maximum being 45. So the difference in the maximum and minimum is 10 times more, it is 1 millimeter. In classical physics, in principle, the measurements are possible with 100% accuracy. But in experiment, however better instrument you can use, having better resolution, there is always a limit to the precision and accuracy of measurement. And one of the factor causing the limit in precision of accuracy and measurement is the list count or resolution. A surface, for example, which appears smooth to you because of our poor resolution of eye, will not look so if the same surface is probed by scanning probe microscopy. That similar example is that for a carpenter, the decision of smoothness measured by looking at it or touching the surface is quite fine. But for scientific exploration of a surface, the better instruments are required having much higher resolution. But the higher resolution cannot guarantee the better precision and better accuracy in measurement. I am repeating that. And to understand that, we will have to understand the error and what causes the error, and understanding error will help us the understanding precision and accuracy. There are three broad types of errors: systematic error, random errors, and blunders and gross errors. Blunders and gross errors are not desirable at all, and if you are sure that the measurement which you have performed include blunders or gross error, it is better to reject the measurement and perform a new measurement. All measurements which you make should be free of blunders and gross errors. But the two important errors, systematic and random error, now we will try to understand, and then we will make attempt to minimize or discuss how we can minimize systematic error and how we can minimize random error. Systematic error, as the name suggests, have a systematically you can study and detect them. But the random errors involve certain random phenomena which you cannot predict and which you cannot know, but the error are there which you observe in the experiment, and there is a technique to minimize the random error. So, first example of systematic error. In fact, it is a category of systematic error. The major category of systematic error is the instrumental. First example which I am giving here is that of the list count error. The list count error is a systematic error. The smallest value that can be measured by the measuring instrument is called the list count. We have earlier discussed the list count of the ruler scale is 1 millimeter, that of vernier scale is 0.01 millimeter we could achieve in the shown vernier in the earlier talk, and that of the micrometer screw gauge is better than that. So, list count error, if you make an measurement by using the ruler scale, you cannot have better accuracy than the list count. So, this definitely there will be an error in the course of measurement of the order of the list count, and that is known as list count error. And we can minimize the list count error because we know the list count, and we can look for and develop and make new instruments which have lesser value of list count or better resolution. The second type of error, systematic error under the category instrumental, is the zero error. Zero error is defined as the condition where a measuring instrument registers a reading where there should be no reading at all. So, corresponding to zero reading, in actual case of the standard or true value is 0, but the measured value is non-zero, it amounts to a zero error. It can be both positive as well as negative in different cases. In case of vernier caliper, it occurs when a 0 on man scale does not coincide with a 0 on vernier scale when you cross down the vernier scale, and it is important therefore to calculate zero error. As once you know the zero error, you can tackle it by making appropriate correction in the readings by either adding or subtracting, as we will be discussing shortly. By this example, the zero error in a screw gauge is shown here. What you find that in the particular leftmost image, you find that when the stud touches the spindle touches the stud, in that case the two zeros are perfectly aligned. You can achieve this touching of spindle to the stud by using the ratchet which was described in the last talk and on the screw gauge. So in the zero error, the zero of the base scale and the zero of the circular scale are in agreement with each other and they coincide with each other. Therefore, we can say the error is not present, zero error, and it is a case of no zero error. But sometimes what you find that at that particular moment it is already showing a reading of two subdivisions as shown in this diagram of the positive zero error. Since it is showing already a reading where the reading should be 0, it is showing a reading of two subdivisions of circular scale, and two subdivisions of circular scale, if the list count is 0.01 millimeter, will correspond to an error of 0.02 millimeter in the positive value, because it is showing and so if you have to correct the reading, then you will have to subtract. In case of positive zero error, for achieving the correction, you have to subtract the positive zero error from the observed value. There can also be a negative error, because in the next diagram you are finding that the 0 is in alignment with the 44 and 46, and therefore 4 more circular division rotation for 4 subdivision would be required to make it 0, and it is a negative 0 error. And in this negative 0 error, since the 4 subdivisions are above the 0 level of the baseline up to 0 mark of the circular scale, we say the reading is a negative 0 error involving a negative 0 error of 4 subdivision. If the list count is 0.01 millimeter, it will amount to equal to 0.04 millimeter negative. And in course of measurement, if you want to make correction of 0 error, you will have to add the negative 0 error value to the reading which you get in the subsequent measurements of whatever is involved, maybe the diameter of a thin wire. The third kind of systematic error is that there are marks and on the scales, and calibration is required of every instrument, and calibration of a instrument can be achieved by using another instrument of better standard or a standard which has been defined for the standard of that measurement. So calibration is very much essential, and calibration is not for the instrument as a whole. For every mark of display on the system or instrument, we have to find the error and keep record of that error. So in the process of calibration, the error is determined by comparing the measurement of the instrument with the measurement of either actual standard measurement or measurement made by the standard procedures and standard methods, and which are more accurate, and in that case we can arrive at the calibration record for the particular instrument. Normally a correction card is kept with instrument and it is used for correcting the error which is because of calibration. You find that there is an error, and this significant error can be accommodated very well by using this correction card, which shows you that if reading on the display is something, what reading should be taken, because based on the comparison with the measured by the standards. So calibration error is also one of the important instrumental systematic error. The fourth type of instrumental systematic error which I am now describing is of several types. There are many reasons which can cause instrumental errors, like misuse or mishandling and neglect of the instruments. If you use instrument in improper manner, not following the protocol, not handling the instruments properly, not doing what is required to be done, then you are neglecting certain aspects of the measurement, then you are bound to get certain instrumental error. There are instrumental error also arising because of environmental change, such as temperature or humidity. Since environmental change in the laboratory at times cannot be avoided, in those situations the measurement, if made at different temperature or different humidity level, may differ in some of the cases. So the instrumental error may arise because of environmental changes. Similarly, the exposure to harsh conditions such as corrosive substances or extreme temperature can also cause the error. The other cause of the error is sudden mechanical or electrical shock or vibration. The frequent use and natural calibration degradation over time, because if you are using, for example, a vernier calipers for a long period of time, then there may be a natural calibration degradation, and which may cause a sort of instrumental error. But other than the instrumental error, also we can have systematic errors arising out of procedural methods or procedural errors. Procedural errors occur when the experimenter does not follow the methodological protocol of the measurement and make compromises in following the protocol. and often precautions are specified with the protocol, but a observer or a measurer, a person who's performing the experiment ignore a precaution, then that can also lead to a procedural error. Procedural error can be minimized by improving the techniques, by inculcating or by having the discipline of measurement, by following the methodological protocol strictly, by obeying all precautions. So we can minimize procedural error in many cases, and in some cases procedural error may be very difficult because the procedures prescribed for a course of measurement is ensuring that certain kind of error cannot be minimized by the change in the procedure or by the way the procedure has been designed. Then there are certain errors which are neither because of instrument or not because of procedure, but because of the person who is making the measurement, and they arise due to an individual's bias, his lack of proper setting of the apparatus, or individual carelessness in making observations or reading observations, and without observing proper precautions. There can be many reasons for personal error. And as we perform experiments in science or in physics, then we get better expertise to perform experiments in perfect manner, and the personal error can be minimized. A new person who is performing the experiment for the very first time is more likely to involve more personal error. But all these systematic errors, whether arising due to instrument or due to procedure or due to personal reason, these errors can be minimized, and we should try to detect and minimize the error as prescribed earlier. Also, I will add few things to it. Systematic errors, though difficult to identify at occasions or times, but can be identified and can be corrected by appropriate mechanisms. The systematic errors are the errors which remains unchanged even if you make repeated measurement. So for example, if there is a zero error in the vernier calipers or screw gauge, then it would affect even if you make the measurement 10 times or 20 times of the same quantity by using the vernier caliper, you cannot get rid of the zero error. So systematic error remains unchanged even if you make repeated measurement. Therefore, no statistical analysis of the data set will eliminate the systematic error or even alert you that a systematic error is involved in the measurement. Systematic error can be located and minimized with careful analysis and design of the test conditions and procedures by comparing your results to other results obtained independently, or either using different equipment or different techniques, or by using same equipment and similar technique but by a standard procedure, or by trying out an experimental procedure on a non-reference value and then adjusting the procedure for the values which you wish to determine, or until the desired result is obtained, achieving a kind of calibration in the process of the measurement. Calibration, when feasible, must be involved in making the measurement, and it is the most reliable way to reduce systematic error, because in process of the calibration we are calibrating the available instrument with the standards or the standard instruments readings, and that's why calibration is a good way of reducing systematic error, and the zero error can be easily corrected as pointed out earlier. Now, for example, I give you a case, a digital bathroom scale. A digital bathroom scale is a scale on the floor which a person stands on, and the weight is shown on an LED or LCD display. I hope that you have used a digital bathroom scale to weigh yourself, and the calibration of the digital bathroom scale is generally described in the technical manual and user manual available with the digital bathroom scale. One should go through it. The first step in calibrating the scale generally involves calibrating the zero, which means that it should show zero when there is nothing on it, and that can be checked, and by following the procedure described in the technical manual or user manual, you can correct the zero error if present in such a digital bathroom scale. The second step is to do calibration with a non-weight, and you should use the non-weight because each scale has certain maximum value, and so as close to the maximum value, if we choose the calibration point, that is better. And later we will come to know that it is better to calibrate at many test points. But for example, you can calibrate a digital scale which you are having from your own weight, that you can visit a doctor's office or use a better scale which is providing highly accurate value for measuring your weight, and just after that immediately measure your weight on the bathroom scale and you can make the correction. But even if we have calibrated the zero and we have calibrated a particular weight for the digital bathroom scale, one cannot ensure that in between the two values all the measurements will be reliable or will be accurate or will be involving not any error. Generally the scale is linear, so from the 0 to the, for example, if my weight is calibrated and it is 66 kg, then the 33 kg will be at the midpoint of this line 0 to 66, and different readings will be shown, I expect. But what I may find in actual case is that the reading is different, and I have calibrated it for 0 and 66 kg, but at 30 kg or 33 kg or 40 kg it is showing error in the measurement. Then because the measurement readings which will be displayed will be based on this straight line from 0 to 66, but the actual value is not in alignment with it. This is called linearity issue or non-linearity or unlinearity of measurement. So even the 0 and full span are corrected, there may be errors in the middle of the range, and which is referred as linearity errors or unlinearity or non-linearity. Generally, the test points are selected so that they are equally distributed throughout the range and we can minimize the unlinearity or non-linearity. No test point can be used for the typical range of usage of the instrument, but it is an important issue. And the similar issue is that of hysteresis. Hysteresis is the difference in the indication when a test point is approached with increasing or decreasing weight. To find out any hysteresis issues in the instrument, you need to calibrate with increasing and decreasing points separately. What I am explaining in this diagram is that if you are increasing weight from 0 to 66 kg, it is following this curve, and when you decrease the weight from 66 to 0 kg gradually, then it follows a separate curve, and that is called hysteresis. In a weighing test, when increasing or decreasing the load, it is important not to overshoot or undershoot the load. This means that when you increase or decrease the load, you must approach each test point with either increasing or decreasing weight gradually, and the hysteresis is a kind of error present even after calibration and should be discovered, and appropriate correction should be taken into account by doing calibration at large number of points on the measuring scale. Another issue with the weighing balance or the bathroom balance is that where to put the load. So it may have a platform either rectangular or circular, and if you put the weight at the center, then the readings may be different than if you put the weight at different points on the area. So that is very interesting thing, and sometimes the result of a weighing instrument can vary slightly depending on if the load is placed in different location on the load receptor. In order to test how much effect the location of the load has, the eccentricity test is performed, and you place the load at different points and find the calibration for each of the point. But it is always better to follow a discipline and place the load at one point only, say number 1, and ensure that the calibration record which you have created is for that particular point. But eccentricity test is also desirable for minimizing the systematic error. The other errors which are of importance, I have already said, are random errors. The random errors are those errors which occur irregularly and hence are random in nature with respect to the sign of the error as well as the size of the error. And these errors cannot be therefore systematically predicted by a theory, and we cannot make a study of it directly. But there is an easy way out, because random error involve random regions, and these regions we believe are so random that we can minimize the random error in experimental measurement by repeating the measurement, and after performing the measurement many times, we can take the average value as the value outcome of the measurement. Instead of considering the individual measurement, what we will do, we will make many measurements and treat the average value of all the measurement as the value of the measurement. These changes may occur in the different values which you measure because of the measuring instrument or because of the environmental conditions, and there may be many unknown reasons for arising of random errors in experimental measurements. But simple way out of experimental error, random error, is to minimize the random error by using repeated measurement of the same physical quantity of the same system. And in random error means that we may not get same value, however we are repeating the measurement and we are getting different values, and because of some random nature associated with the measurement. And that is why repeated measurements are done. And if you have to determine time period of a simple pendulum, then you can determine the time period for 20 oscillations, but one single reading of time period of 20 oscillations will not be proper, and it would be better that if you make for 20 oscillations time period reading 10, 20, 30, 40 times, and then take average value as a time period for 20 oscillations, and from that you can compute the time period for one oscillation. So the average value should be used as the outcome of the measurement. This value may not be one of the value in the set of measurement, and that is a characteristic that may happen because of the way average is defined in statistics. It doesn't mean that the average value should correspond to one of the answer which you get in the set of measurement. But generally we find that the random errors behave in such a manner that if we plot the measure value, then generally we get the curve which is called curve of Gaussian distribution, and the spread of the Gaussian curve indicates precision in the measurement, and greater the spread, less precision is there or less precise is the measurement. Best precision of zero width is impossible to achieve in most of the cases of measurement. However, large number of repeated measurement you can make, but it is difficult to get best precision of zero width, and the errors like blunders and gross errors should be ignored before considering the average value. So in determining the average value, you should ensure that the data which you have collected involving blunders and gross error is not considered in determining the average value. So even with the available resolution and repeated measurement carried out to improve precision, the measured average value may not be accurate value due to systematic errors or other unknown reason. The difference between the measured value and true value, as I told you earlier, is called error, which can be positive and which can be negative. Remember the difference. Error is measured value minus true value. But when you perform the experiment many times, then you get a Gaussian curve distribution like this, and the width of the distribution is an indication or indicator for the precision. Smaller is the width, better is the precision. Here it is shown that the average value is this much and the true value is different than the average value, and which tells you that there is an error and 100% accuracy is not accessible in this experiment. Neither you can have it the precision such that this width becomes 0. So after understanding this, we have an understanding of errors, and we know that errors cannot be avoided also in the experimental measurement. Therefore, it is better to show error bars in the graphical representation of the data which you have collected, and you would find such error bars in many curves, in many graphical representation. Here you find that the error bars are of different thicknesses or different range. Here the error bars are small, in this case error bars are large, and they are drawn on the basis of generally one standard error or one standard deviation error, and there are parameters like confidence level defined in statistics which are used to describe the error on the graphs by using error bars. And I will not describe the statistics in detail here, but definitely would give you an impression about how we define certain quantities like standard deviation in the statistical manner. But what we wish to achieve in the course of measurement is to have accurate measurement and to have precise measurement, and different results we may get in different experimental measurement depending upon various factors already discussed. Here is an example where I have shown that suppose we are thinking of hitting the bull's eye, and the dots are showing where the arrow has hit on the dartboard, and that is being shown by dot. What you find in this particular diagram, that all the add dots are within the bull's eye, and since all the add dots are within bull's eye, we can say that the measurements is accurate because the true value is the bull's eye, and so measurements are accurate, and since measurements are very close to each other, so they are also precise. So that is what we aim, a more accurate and more precise measurement. But in the diagram on the right to it, what you find that the values are accurate, not as accurate as here, but there are two dots in the bullseye, and in the next region there are 6 dots. So what you find in this case, that some level of accuracy is there, but dots are far away from each other. So distance between dot is far more in comparison to this diagram, and therefore what we say that this is also an accurate measurement because the dots are close to bullseye, but it is not precise, so it is imprecise measurement. You can also have the other scenario where the dots are very close but far away from the bull's eye. So the measurement is not accurate, because accurate measurement means the dots being within the bull's eye, and here the dots are away, but the dots are closer to each other, and therefore we say that this measurement is more precise. So now you have, I hope you have understood it, that if the dots of the measurements are close to each other, then we say that the measurement is precise. If they are away from each other, we say it is imprecise. If the dots of measurement fall in the bullseye area, the target or true value area, we say it is accurate, and if they are away from the target or the bullseye area, then we say it is not accurate. So in this diagram, neither the dots are close to the bullseye nor they are close to each other, and so the measurement is inaccurate and imprecise. And inaccurate and imprecise measurements shall be avoided, and accurate and precise measurement should be aimed at. So you have to understand your experiment very well. You have to be top on your experiment, understand each and every aspects involved in the measurement, the functioning of the instruments, the protocol and everything involved in the course of measurement. And you have to keep an eye on all those things. So having the correct tools to collect and analyze your data is also very important when we make use of repeated measurement, as understanding the accuracy and precision of your data depends upon the tools which you use in understanding the data statistically. A single step in the right direction is the first move, is the second move and the third move and so on. So what we do in physics or science, that for improving or keep on improving the experimental measure, we first take a single step in the right direction, which is then followed by another single step in the right direction, and which then will be followed by another single step in the right direction. In this systematic step-by-step manner, we have achieved that most of the physical quantities which we have defined much earlier and now can be measured more precisely, more accurately in experiments. In advanced experiments, generally we can achieve a high degree of accuracy and a high degree of precision in measurement. So in a school experiment, maybe it is not possible all the time to achieve high degree of accuracy and high degree of precision. But that is our aim, improving day by day. Science is moving ahead in this manner, the experimental science, that we make an attempt to move in right direction so that we can have better, accurate and better precise measurement. Now to define the set of quantities to understand the error, I'm explaining now the definitions and other things. In a series of measurement, let the ith measurement be denoted by A with subscript I. So here I is being used as an index and AI indicate the ith measurement of a quantity called A, value of which is AI in case of the ith measurement, and where say I varies from 1 to n, where n can be any natural number, 20, 50, 100, whatever you want. Then average value of measurement we have to define, because we have n number of measurements. So first add all those n number of measurement and divide it by n. That will give you the average value of measurement. So it is a very simple mathematical calculation. Add all the values of measurements. Remember, every measurement will not give you the same value because of the random nature of errors involved. The measurement values will be different. So AIs are different maybe from each other, but you can obtain a value which is average value. But this average value may not be one of the AI out of the set of the AI which you have, the n members of AI you are having in that set, and the average value of A may be different than one of the AI which you have in this set. Then we define a next quantity. So average value will be often taken as true value when we minimize the random error, and let us assume that we have already minimized the systematic error and all corrections and calibrations have been achieved and done in arriving at the values AI. So systematic errors have been avoided, and then we repeat the measurement for avoiding the random error, and then we can treat the average value as a true value. And then we define error. Error earlier was defined as measured value minus true value. So now I am using measured value error in the ith observation or ith measurement as the measured value minus the average value as the true value. So that will be denoted by delta AI. So the deviation or error in the measurement delta AI is by definition AI minus the average value of A, all readings. Generally we use, because errors do have sign positive or negative, what we call absolute error or absolute deviation. Absolute error or absolute deviation is just the magnitude or modulus of the difference in AI and the average value of AI. So it is the difference of deviation. The magnitude of the difference is called the absolute error. It would always be positive. And once you have the absolute error, in the similar manner you can find the absolute error for all the measurement, and then by adding the absolute error of all the measurement and dividing it by the total number of measurement n, you can define or get the quantity which is called mean deviation. So mean deviation is the average of the deviation in all measurements. So you make n number of measurements, add the absolute deviation of each of the measurement and then divide it by n to arrive at what we call mean absolute error or mean deviation. You can also find similarly mean square deviation. Mean square deviation, because the square of deviation would always be positive. So mean square deviation can be obtained by squaring this particular quantity deviation and then taking the mean. So adding all the square and then dividing by the total number of measurement. So mean square deviation can be obtained in this manner. We also define relative error. Relative error is the error. For example, absolute error is the modulus of delta AI, and if you divide it by the value AI, then it can be called relative error. Relative error generally is defined as the mean deviation divided by the mean or average value. So average value of deviation divided by the average value can be defined as the relative error, and relative error is in fractional form, and it is generally in fractional form expressed, and you can express it also in percentage form by multiplying the relative error with 100, and you can express it in percentage form. Standard deviation can also be defined. We have defined mean deviation, mean square deviation. The root of mean square deviation is called standard deviation. Often in your books you will find the mention of 1 standard deviation, 2 standard deviation away, and things like that. So how standard deviation is defined? These definitions, all which we are using here, are from the subject statistics, and you may learn these things, and you may have already calculated such things in your school curriculum of statistics. So the standard deviation is nothing but root mean square deviation. So this is the mean square deviation, and if you take square root of that, it is called standard deviation. Now, to understand the algebra of the errors, the algebra of the errors can be understood in this manner, that suppose you define a quantity P like A plus B minus C minus D. So you are expressing P in terms of A, B, C, D, but the definition involves only addition or subtraction. So like here, P is A plus B, so A and B are added, and out of that then C and D are subtracted. So in that case, the absolute error can be very easily related between the absolute error in P can be related to absolute error in A, B, C and D by this relationship, which tells you that absolute error in P is sum of the absolute error in A, B, C and D, and you have to keep positive sign here irrespective of the sign in the formula of P. So whether it is minus C or plus C, you will have plus delta C here. But when two quantities are multiplied or divided, it is better to describe the algebra of errors in terms of relative error, because we have a simple relationship in terms of relative error. And suppose P is given by multiplication of A and B and then divided by C, then we can write P equal to AB divided by C. Then the relationship in the relative error of P is that relative error of P is equals to relative error of A plus relative error of B plus relative error of C. Again, whether it appears in numerator or denominator, the relative errors will be added. But sometimes what you may have, that you can have a formula like where P is A raised to power n, B raised to power n, C raised to power k, whatever the number. So the relative error in a physical quantity raised to the power k is the k times the relative error in the individual quantity, which means suppose the formula of P is A raised to power n, then by using this formula A raised to power n means multiplying A n times A into A into A n times. So you can very easily verify this relationship, that based on this formula that the relative error in P will be n times the relative error in A. Now I describe an example here for doing the calculation. Here the formula of P is given as A square B cube divided by C square and square root of F. So it is given that the quantities A, B, C and F, here it is by mistake written D, but it should be F, A, B, C and F is 1%, 2%, 3% and 4% respectively, and the question is, what is the percentage error in P? If the value of P turns out to be 2.4356, to what value we should round up the value? So the formula is given, and by using the previous rules you can very easily write that the relative error in P will be twice relative error in A plus thrice relative error in B plus twice relative error in C plus half relative error in F. Half because square root, twice here because of C square, and this is A is also square, so twice, and B cube because the power is cube here, so 3 times the delta B by P. And the relationship, because difference between the relative error and percentage error is just a factor of 100, and so we can say percentage error in P is also given by similar formula, twice the percentage error in A plus 3 into percentage error in B plus 2 into percentage error in C plus half into percentage error in F, and the values are substituted here, and you come to the number that the percentage error in P in this particular question will be 16%. Now by mathematics you can easily work out percentage error in P, which is 16%, will amount to 0.3897. So 16% of 2.4356 is 0.3897. So you know that the error is involved up to this digit, one digit after just after the decimal point. So even if the reading is 2.4356, we have this general rule that we can keep only one uncertain digit in the reporting of the result, and so 2.4356 should be rounded off to 2.4, and had it been 2.4756, then it would have been rounded off to 2.5, and these rules are important. Now I come to the topic of significant figures. The result of measurement should be reported in a way that indicates the precision of measurement by specifying a number that includes all digits in the number that are non-reliably plus the first digit that is uncertain. So that is what is the rule which we have adopted, that all the results of the measurement should be reported in that manner, that it should not involve more than the reliable digit plus one uncertain digit. The reliable digit plus the first uncertain digit, the number of reliable digit plus the first uncertain digit will be known as number of significant digits or significant figures. For example, using the common ruler, if we have measured that the length is 5.2 centimeter, you can also say length is 52 millimeter, or you can say 0.052 millimeter. All the three are correct, but the significant figure is 2 in all these examples. Whether you write 5.2 centimeter or 52 millimeter or 0.052 millimeter, we will get the same number of significant figure, which is 2. We will learn how to compute the significant figures, what are the rules shortly. A choice of change of different unit does not change the number of significant digits. So outcome of measurement being 5.2 centimeter expressed as 52 millimeter or 0.052 millimeter, the number of significant figure remains 2, but the unit which you are using you have changed in the 3 kind of reporting. But if you specify the same reading as 52.0 millimeter, then it means it is involving 3 significant figures, and if the measurement is not involving 3 significant figures, then this would be a wrong way of expressing the result. Down numerically you can argue that 52 millimeter is same as 52.0 millimeter, but you are not allowed, because 52.0 millimeter indicates there are 3 significant figures and 52 millimeter indicates there are 2 significant figures, and you have a knowledge that the measurement which you are performing can be at the best the first digit is reliable digit and the second digit is unreliable, because as you know in case of ruler scale the list count is 1 millimeter. So 50, the first digit 52, the 5 is reliable digit and the digit 2 may involve some error because the list count is of the 1 millimeter order. It can be 51 millimeter or 53 millimeter or any value between 51.5 to 52.5 the true value may be. But since we have measured by using a list count of 1 millimeter, we cannot specify the value even if we have taken the repeated measurement in with better resolution, better significant figures or more significant figures. So how to get the significant figures, how to read how many significant figures are there. For example, the expression 1, 2.54 involve all non-zero digits, and all non-zero digits are significant. So you say that in 1, 2.54, if you are expressing some quantity as 1, 2.54, so 12.54, then all the 4 digits are significant. All the 0 between two non-zero digits are also significant. So if in some measurement you get 5205.7, then you say that the significant figure is 5. Not only 5257, but the 0 which is in between would also be considered significant. So all the zeros between two non-zero digits are significant. But the zeros which are not between the two non-zero digits, we have to check how to deal with them. If the number is less than 1, and suppose you express a number like this 0.0005250, so this is a number which is less than 1, and there are 4 zeros before the 52050, and which means to the left of this particular 5 there are 4 zeros. All these 4 zeros will not be considered significant. So the number of significant figure in this case is also 5. So what we are saying, that the 0, if you have a long 0 on the left of the decimal, or if you have 0 on the right of the decimal, immediately right of the decimal points, all those zeros will not be considered significant. So I repeat, the zeros on the right of decimal point but to the left of the first non-zero digit are not significant. The underlined zeros in this example are not significant. The terminal or trailing zeros, even if you are not using decimal point, are not significant. So if you write the value as 52000 micron, then the number of significant digit is only 2. The 3000 appearing after 52 will not be considered significant. The trailing 0, however, becomes significant, and suppose you write it as 52.0, and that is why in earlier example I have said that 52 millimeter is having 2 significant figures, but 52.0 after decimal we are having the 0, and 52.0 is indicating that there are 3 significant figures. So based on the knowledge of experiment which you have performed, the measurement should be described by using correct number of significant figures only, and if need arise, then you have to round off the quantities. And how the quantities will be rounded off, that you should understand, and I will come to that. But the scientific notation explained earlier in presentation, the mantissa involves the significant digits other than what you have on the left of the decimal point, because I have said on the left of the decimal point in scientific notation the modulus of the number can be between 1 to 10 only. So the digits in the mantissa are significant, and that digit which you have in coefficient, the modulus of the coefficient, is significant in this notation. But there are rules of significant figures which we can make use of in understanding it. In multiplication or division, the final result should retain as many significant figures as are there in the original number with the least significant figures. Suppose you multiply two quantities A and B. 2 is having 2 significant figures and B is having 3 significant figures. Then after the multiplication, A, B should be specified up to 2 significant figures only. Now the numerical value which you calculate manually or by using calculator, you can have many digits coming out of the calculation, but only the 2 significant figures corresponding digits should be taken into account or description. So in multiplication or division both, the rule is that we should use the least significant figures in the quantities involved in multiplication or division. So even if say I am dividing A by B, A is having 3 significant figures and B is having 2 significant figures, then the significant figure of the output A divided by B would also be 2. But in addition or subtraction, a different rule we have to use, and that is that when we express quantities by using decimal places, then if in the first quantity or any quantities which are being added, the final result should retain as many decimal places as there are in the number with the least decimal places. So which means what? That if I am adding 1.2 to 1.35, then I can say that 1.2 plus 1.35 is only 1.5, and if I write 1.55, that will be making extra information. But since this is 1.2 plus 1.3, so it is 1.55, and in case of 1.55, in fact I have to round it to 1.6. So 1.2 plus 1.35 will be 1.6. How to carry out rounded off? That is explained that if the digit which is to be rounded off, so suppose we want to round off to 3 significant figures only, all these numbers. So the number here in the end 5.738, the digit which is to be rounded off is 8, and since it is greater than 5, so the precedent digit will be raised by 1. So 5.738 when rounded off, because 8 is more than 5, so will be rounded off to 5.7. But if the digit is less than 5, for example in 5.743, then we will drop this is digit 3, and it will be described as again as 5.7. So whether 5.743 or 5.738, both will be rounded off to 5.74. Interesting case arise when the digit is 5. Then you have to look at the precedent digit also. And if it is an odd digit like here 735, so precedent to 5 is the 3, which is an odd number, then you have to increase the precedent digit and make it 5.74 here. But if the precedent digit is an even digit, then you may not do any and just drop that digit. So 5.745, 5.735, 5.743, 5.738 all will be rounded off to 5.74 based on this rounding off rule, and which you must remember. So the message is that while reporting the results, while doing calculation, due care must be taken of significant figures. In fact, using more than significant figures permitted value is just cheating, a sort of cheating, and will lead to more complication. So we have to follow the healthy practice of following the rules of significant figures and specifying only one unreliable digit along with the reliable digit in our description of the outcome of any measurement. Now the measurement we have earlier noted have become very important, because the theories which we have in physics or any science theories can be verified in experiment, and the agreement between theory and experiment is checked in experiments, the theoretical prediction, and if the experimental observations matches each other, then we may tentatively say that theory is in agreement with the experiment. But in fact, this agreement is always tentative, and the main reason is that their measurement involves issues like precision and accuracy. Due to further advancement in the methods of measurement or instruments of the measurement, the precision and accuracy can be improved. So if I find that a particular theory is in agreement with experiment today, if tomorrow I do the experiment with a more precise, more accurate, it may happen that I discover a discrepancy between theory and experiment. So what we say that an experiment can be used to falsify a theory, and all theories of physics must be falsifiable, and therefore every theory has some provision by making some experiments we can prove it wrong. But the agreement never ensures that the theory is correct. It is always called tentative. So there are no final proofs of the theory from the experiments. The experiments can be, however, used to reject or falsify a theory or theoretical prediction. That is why experimentalists are all the time interested in improving the precision and accuracy, so that to a better level of precision and accuracy, the ideas and implications or theoretical prediction can be checked in experiments. The final topic for today's talk is dimensional analysis. I have already defined the 7 base quantities, the international system of quantities, and the other quantities other than base quantities are expressed in terms of 7 base quantities by using the approach of dimension. The 7 base quantities are length, which has dimension of L, and the dimensions are shown within the capital bracket. So length dimension symbol is capital L within bracket. The mass, the dimension symbol is capital M. The time, the dimension symbol is capital T. Electric current, the capital A. Thermodynamic temperature, capital theta. Amount of substance, and luminous intensity, J. All capital and within the capital bracket. So they denote the dimensions of these base quantities. Base quantities have their own dimension, and that cannot be expressed in terms of dimensions of other base quantities. But all other quantities, which we call derived quantities, will be having dimension in terms of the dimensions of base quantities. And that is what we have learned. We have defined velocity, and velocity is having dimension of length divided by time, and we say dimension L t raised to power minus 1. Similarly, the acceleration is having dimension of length L t minus 2, and L t raised to power minus 2 indicate that it has one dimension of length and two reciprocal dimension of time. And that of force you can obtain from the acceleration, because later we will define force in terms of mass times acceleration. So it is very easy to see that the dimension of force is mlt raised to power minus 2. That of electric field can similarly be obtained from the force and the dimension of electric charge. The electric current is the base quantity and not the charge, and the electric charge will have a dimension of time into electric current, so TA, and the dimension of force is ml t raised to power minus 2. So the dimension of electric field turns out to be ml t raised to power minus 3 a raised to power minus 1. There is again a typo is written 2 times, ignore that. So there are certain typos always occur when I make presentation. So ignore all the typos. Then we can now find the dimension of any derived quantity in the same manner. And suppose you are interested in determining the dimension of the gas constant, the molar gas constant, which is used in the expression PV equals to nu RT. So that can also be obtained in terms of the dimension of pressure, volume, quantity in moles, and temperature. Since the formula of R is PV divided by nu T, and which means the pressure and volume are in numerator and the quantity of moles and temperature are in the denominator. And it's very easy mathematical exercise to using these values, that the pressure has dimension of m L raised to power minus 1 T raised to power minus 2, volume L raised to power 3, quantity in moles and temperature theta. You can verify that the dimension of the gas constant is m L raised to power 2, T raised to power minus 2, theta raised to power minus 1, and raised to power minus 1. The dimensional analysis is very helpful. I have already made use of dimensional analysis when I said that if the position is given as a function of time in a particular example, x was given as a plus bt plus ct square plus dt cube, and there I have described that each quantity on the right hand side should also have dimension of the quantity on the left hand side, that is the position. So a and bt and ct square and dt cube should also have same dimension of length, and therefore a should have dimension of length, b should have dimension, because bt should have dimension of length, so b should have dimension of length divided by time, and similarly c should have length divided by time square, and d should have length divided by time cube, so that each term on the side is having same dimension, and that is the most basic rule of dimensional analysis, and it is called the rule of dimensional homogeneity. Only commensurable quantities, which means physical quantities having the same dimensions, are called commensurable quantities, and only commensurable quantities, that is quantities having the same dimension, may be compared, equated, added, or subtracted. So any expression which is involving equation, equated, or adding or subtraction, this dimensional analysis rule should be applied. However, we know that the dimensions form an abelian group under multiplication. A group is a mathematical concept. An abelian group means commutative group, and every group involves a set and an operation. So what I have said here, an abelian group under multiplication, which means that we may take ratio or multiplication of such quantities, incommensurable quantities, which means in case of multiplication or taking ratio or division, the incommensurable quantities may be involved. And that is what we have already done, that when we defined average velocity was defined by taking ratio of the displacement over the time interval. Displacement was having dimension of length and time interval is having dimension of time, and that's why the average velocity was having the dimension of length time inverse. Taking a derivative with respect to a quantity also adds the dimension of variable with respect to which you are differentiating in the denominator, and that is why when you define instantaneous velocity as the rate of change of position vector with respect to time, then the position vector is in the numerator and the differentiation you are making with respect to time so would be in the denominator, and the dimension of the quantity called instantaneous velocity is therefore LT inverse. Likewise, taking an integral adds the dimension of the variable one is integrating with respect to in the numerator. So for example, integration of acceleration with respect to time will give you the velocity. The dimension of acceleration is Lt minus 2 or t minus t raised to power minus 2, and so when you multiply it by 1t, then you get the dimension of velocity, which is Lt minus 1. The units of the quantities, derived quantities, are derived on the basis of the units of base quantities using SI unit system. So this dimensional analysis approach is very helpful, and you must use it in understanding the equations which we will have in our discussion of the course of physics. Every equation which you have must be dimensionally consistent. That is, the dimension on left hand side should be equal to the dimension on the right hand side. The dimensional analysis also help us in guessing the formula or relationship between two quantities. For example, the velocity has dimensions of Lt minus 1, the acceleration has dimension of Lt raised to power minus 2, and the height has the dimension of L. So we can make an easy guess that in the problem which we have discussed earlier, the projection from the ground in the vertical upward direction, if suppose we project something with initial speed u and it attains a maximum height hm and the acceleration due to gravity is g, so what we can make to conclude that the u would be in some sense related to the square root of g and hm, because the square root of g and hm, product of g and hm, is having the dimension same as that of the u, the velocity dimension. Again repeating, the dimension of acceleration due to gravity is L t raised to power minus 2, that of hm is L, so that of the product of GHM is L raised to power 2, t raised to power minus 2, and when you take the root, then the dimensions become L t raised to power minus 1, and that is the dimension of velocity. But you cannot get by dimensional analysis this factor of root 2, which is there, and you know why it is there. We have derived this relationship by analyzing the problem. So the projection speed for attaining maximum height hm is given by the square root of root 2 ghm, and this equation is dimensionally consistent because the velocity is on the left hand side, dimension of the left hand side, and velocity is also the dimension of the right hand side, the total, the square root of ghm. So we can make use of it and do certain kinds of problems. Very interesting problems have been described in the literature. I am taking one such example, which is also a solved exercise in the book of physics by Halliday, Resnick and Crane. So an important milestone in the evolution of the universe just after the Big Bang is the Planck time. And I have earlier told you that we cannot know from the Big Bang, the time t equal to 0, to what happened in the first time interval of equivalent to Planck time. So that interval is not permissible as per the laws of the nature, you can't know anything. In fact, any time interval shorter than the Planck time, we cannot get information. So it's not observable. And this is restricted by the laws of nature. But to understand that in better terms, you need to understand the Big Bang theory of cosmology. But without understanding the Big Bang theory of cosmology or things like that, I can make out what can be the relationship of Planck's time in terms of other three fundamental constants. The three fundamental constants chosen here to describe the Planck time is the first, the speed of light, which is being denoted by c, the Newton's gravitational constant denoted by capital G, and Planck's constant denoted by small h. Planck's constant and speed of light c have appeared in our earlier discussion also. The Newton's gravitational constant G, to my knowledge, is appearing for first time, but it is a constant which is in the Newton's gravitational law given by this expression F equals to minus g m1 m2 r square. In magnitude scalar terms, the direction of F is minus r unit vector, and so towards each other. So this force, which is called gravitational force exerted by one point mass m1 on another point mass m2, is given by this mathematical relationship, and that involves a constant, and that constant is same, and that's why it's called universal gravitational constant G. And that universal gravitational constant capital G we are using here. Remember, small g is different, capital G is different. So by using ISQ, International System of Quantities, I can describe the dimensions of these three constants C, G and H. These are given here in the slide. C being the velocity or speed of light is having dimension of L T inverse. The G dimension can be obtained from this expression, and it will have same dimension as force multiplied by r square divided by mass square. So the dimension of G works out to be m raised to power minus 1, L raised to power 3, T raised to power minus 2. And similarly, from the relationship energy E equal to h nu, and you can find the dimension of nu is 1 upon time, and dimension of energy you know is m L2 T minus 2. So you can find then the dimension of H is m L raised to power 2 T raised to power minus 1. Now to make a guess of the relationship between the Planck constant and the C, H and G, let us assume that Planck constant is Planck time, not Planck constant. Planck time is proportional to C raised to power I, G raised to power j, H raised to power k. I, j, k are integers. So let me assume that this is true. Then I can find the dimension of T raised to power Planck time by determining the dimension on the right hand side. So I know that the dimension of Planck time is that of time. Now I determine the dimension of right hand side. So dimension of right hand side can be determined by writing the dimension of C and raising it to the power I, writing the dimension of G and raising it to the power j, and by writing the dimension of the H and raising it to the power k. So that is what I have done here. I have written the dimension of C, G and H and have raised them to the powers I, j and k as appearing in the formula which I have assumed. So I get the dimension of right hand side expressible as m raised to power minus g plus k, L raised to power I plus 3j plus 2k, and T raised to power minus I minus 2j minus k. And now the dimensional analysis tells me that the dimension of right hand side should also be that of time, and to make that of time, the dimension or in terms of m should be 0, which means minus j plus k should be 0. Similarly, I plus 3j plus 2k should be 0, and you have that the dimension of t in this right hand side is minus I minus 2j minus k, so put that equal to 1. So we get these three algebraic equations which we can solve. From this equation you get j equal to k, and you can substitute j equal to k and reduce these two couple equations, and you know how to solve simultaneous equations of two variables. If you know that mathematics, you can obtain the values of I, j and k. And what it turns out, if you do the calculation, I am not doing it explicitly here, then I turns out to be minus 5 by 2, j turns out to be half, and k turns out to be half. And therefore we get a formula case for Planck time as under the square root of the whole quantity gh divided by c raised to power 5. So that is the case. And in fact, the correct relationship also involves a factor of root 2 pi square root in the denominator, and the correct expression for Planck time is given here as under the square root gh divided by 2 pi c raised to power 5, and then by substituting the known values of this constant, these constants are known very precisely, so by substituting the known values of this constant, we can determine the Planck time, and which value is given 5.391247 into 10 raised to power minus 44 second, a very small time interval. And as I have said earlier, that you can't know what happened between t equal to 0 to t equal to Tp after the Big Bang cannot be known, and similarly anything which happened in the time interval less than the Planck time cannot be known by us because of the laws of nature, which you will be able to understand towards the end of this video lecture series. So a long journey we have to make. But with this, I conclude my today's presentation, which was focused on errors, significant figures and dimensional analysis. In the next talk, I would be describing vectors in 2 and 3 dimension and their sample algebra. So that we can have a knowledge of vectors in 2 and 3 dimension, we can very easily describe the kinematics in 2 dimension and then kinematics in 3 dimension in terms of these vectors, making use of these vectors. So I would be doing that in the next talk. I hope you are liking my video lectures. Please click the like button if you like the video lecture. You can subscribe my YouTube channel A4 Science by clicking the subscribe button, and you can also click the bell icon to get the notification regularly. Thank you for being with me in this video lecture series.